So next up, we're going to try to prove that this transformation is also an isometry or asymmetry or whatever, that it preserves distances. So let's just show you what this thing does for starters. And we've looked at this already, but we'll look at it again. So all it does is it's going to flip the two coordinates, and it's going to change the old y, new x. It's going to change its sign. So for example, 1, 3 becomes negative 3, 1. And 3, 3 becomes negative 3, 3. And 3, 2 becomes negative 2, 3. So let's see, it's negative 2, 3, negative 3, 3, and negative 3, 1. So there's our new triangle right there. And if you haven't noticed, it is a rotation, a 90-degree rotation about the origin. Okay? And you'll notice that this triangle is the same as that triangle. All the side lengths stayed the same. So it did seem to keep the side lengths the same, right? It's distance or length preserving, say. Okay, so we're going to use distance formula again to set that up. And we're going to say, well, I've got point M, which has coordinates A, B, and point N, which has coordinates C, D. And then we're going to go to M prime, which is going to be negative B, A, and N prime, which is negative D, comma, C. Okay? And we're just going to find the distance between these 2 points, the distance between these 2 points, and show that they're the same. So let's see. Distance between these two is square root of A minus C squared plus B minus D squared. And we're going to say that that's equal to, we've got negative B minus negative D squared plus A minus C squared. I kind of ran into some stuff over there. Okay. So first thing we'll do, take the square roots away. So A minus C squared plus B minus D squared equals negative B, and I'm going to change this into plus D. B, and that should be a D, plus A minus C squared. Okay. And notice you have two of these, so we can take them away. So that leaves us with B minus D squared equals negative B plus D squared. And we can just flip these around again. B minus D squared equals D minus B squared. And we've been here before. Saw this in the previous proof. Remember, if you subtract one number from another and then you just switch them and you subtract going in the other direction, you just get opposites of each other. Right? So 1 minus 3 is 2. 3 minus 1 is negative 2. And when you square opposites, you get the same answer. So no matter what I put in for B and D here, I'm going to get the same number on either side. But just going to whittle this down to show that it's actually true. So we'll expand each of these binomials. And we get B squared minus 2BD plus D squared. And then over here, D squared minus 2BD plus B squared, and then notice cancel, 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 cancel. 0 equals 0, which is true. And since this is true, we could work this whole process in reverse. And again, since we followed all the rules of algebra, then each statement, as long as we add the same thing to each side, subtract the same thing from each side, the truth of the statement stays the same. And so if this one's true and we have followed all the rules, then the original statement must also be true, meaning that the distance between M and N is the same as the distance between M prime and N prime, which means that this transformation keeps distances the same. It's distance preserving. Okay? All right. There you go. We proved it.